data set, I change to my working directory, and then I load the directory, I load the data set. Right? And then you guys did a tab stat on all the variables. And what statistics did we look at?
Mean, min, max, standard deviation.
And
Say that again?
and I put skew and kurtosis in.
All right, so what am I interested in looking at here? First of all, I'm going to be the really thing that I'm going to be interested in here is I'm going to be looking for my ends. That's the first thing I'm going to look at again, because missing data is really important, right? Figuring out, do we have missing data? Are those data that we have, the data that are missing, the people that they belong to, are they systematically different from the people for whom we have data, right? That's going to be an important thing. So with respect to my age, so I'm dealing with 45-year-old people and I'm studying coronaries. Does that make sense? Sure, it's we're in the at-risk. I'm in the at-risk group. 23-year-olds having a coronary? Sure, why not? 7-year-old? Okay. So a systolic blood pressure of 124. So these people are, relatively healthy on average. However, we got some people whose hearts are really pounding really hard. Right, so I'm interested in looking at these things. Are these things reasonable? So we got something with a cholesterol level of 520. Really high, but plausible, given the sense we're studying some sort of a metabolic cardiovascular disorder. Not a whole lot of variability in height. Right, so that's what I'm interested in here. So our weight, we have some variability in weight. If I'm interested in studying cardiovascular conditions, I'm missing people at the, I'm missing people at the top end of the scale, right? So 260, it's big, but it's not like the 300-400 pounders you might see coming in treatment. And then here we have our coronary, so this is whether or not they had a heart attack, and this is the prevalence of heart attack in the data set. So you guys realize that a proportion is in fact a mean. Okay, so all of these statistics are relevant here too. So I'm basically looking at this to see, what am I dealing with? What does the average person in my data set look like? Right? And are these values reasonable?
And then the skewness and the kurtosis?
The skew and the kurtosis. One of these days, I'm just going to kill myself on that. Okay. So the skew I'm going to be interested in looking at here. So here I have some skew here. So these values here are all positively skewed. So, so here we have, on average, there's going to be some outlierness on the high-end range, right? To make sense of these kinds of statistics, it's better, for me anyway, is to plot these things. And the reason I'm interested in looking at this is, again, getting a sense of who I'm dealing with. Because we can look at the means and we know that we can easily think of distributions that look like this, right? Where the mean is going to be pulled in the direction of the tail. So sometimes the mean is not the best index of central tendency. So if I see a lot of skew, which I don't see a whole lot of skew here, I can begin to think, is the mean a reasonable index of central tendency if we're talking about the typical person? For the kurtosis, I'm interested in looking, is there a lot of variability? This kurtosis above 3, a kurtosis of 3, the standard normal distribution has a kurtosis of 3. So when I have a positive value of kurtosis, that means it's leptokurtic. When I have a very small value, it's platykurtic. Less than 1. Platykurtic, flat, thick tails.
Well, okay.
Yeah.
And so if you see something that's like kurtosis of 3.3, you can sort of visualize that it looks like a normal distribution.
Well, no, it doesn't necessarily look like a normal distribution, but it's got about the same amount of variability as a normal distribution, because it may be bimodal or goofy looking, right? It can have any shape.
Sure.
But the variability is about on par with what a normal distribution would be.
Okay.
Okay.
And what would be high for skewness?
For skew,
What would you consider
well,
high?
anything above 2? Yeah.
Just a-
Just 1.96-ish, 2.
Okay.
What was the opposite of platy curve?
Leptokurtic.
Leftover.
How do you teach people?
Lamp.
Lamp.
Lepto, meso, lady.
Oh, right. So how do you? So here's how I remember what's fat, thick, thin is that you have to leap high over a leptokurtic. And platy is flat like a platypus.
Platypnea.
Huh?
Platypnea.
Okay, sure. There you go. That.
I can't help you with that joke.
Wait, say that. I'm so confused. Lamp and I just heard.
So there are lots of, the mnemonic that I come up with is that in a leptokurtic distribution, you have to leap high over a leptokurtic distribution, right?
Yeah.
Platy, plat, flat. And then apparently there's a thingy-majiggy
And that
she
would
was
be-
talking about.
Yeah, gotcha.
Platy, flat. Meso means middle. Okay, now at this point, I chose the model that I fit was just a simple direct logistic regression because I was interested in the explanatory power of all of the variables simultaneously. Right? But that was my hypothesis. It's entirely possible that you came up with a hypothesis all on your own. You may have designated some of these things as control variables and other things as variables of interest. Did anybody not do a direct logistic regression? Everybody did a direct logistic regression. Fair enough.
I did.
You did. You did not. What did you do?
I didn't do anything.
You didn't do anything. F.
I tried to like group things.
Okay.
Like group them into like high versus low blood pressure.
Okay.
And then logistic regression on those things.
All right.
It didn't come out of this.
It didn't come. Yeah, well, I wouldn't imagine you would.
I made like a BMI variable as opposed to like a height weight.
Okay.
Because like I didn't think that height and weight separate were that meaningful to me.
Mm-hmm. Okay, fair enough.
And it was significant.
Okay, that's great. Great, that's good. Did you write? Well, I hope when you did your write-up.
It was like
that you
every
combined them.
increase of, yeah,
Right,
like you
because-
generated a BMI variable for every increase in BMI. There was a,
But providing a rationale for why you chose a derived variable, BMI, as opposed to the components, its height and weight.
Okay.
That's good.
You treat BMI continuous or categorical?
I treated it continuously.
All right, so can we talk about our discussion we had yesterday?
Yeah.
So Dominique. Such a pretty name, I can't remember. So Dominique and I had this conversation yesterday about categorizing variables, and she was interested in looking at BMI on
Disability.
ICU discharge status.
Mhm.
So I think the statuses were,
Dependent, independent, or partially dependent.
okay, did you all hear that? So her strategy was to take BMI and cut them up into quintiles, cut them up into 5 categories based on some criteria, right? Her hypothesis, her prevailing, I'm not preempting anything, am I?
It's for the next class, but it's fine. Preview is fine.
So she hypothesizes that there's a parabolic relationship between weight and discharge status, right? So she hypothesizes that at the extremes, you're more likely to be in the disabled category relative to the
Normal BMI.
Thank you. Right. Okay. We'll come up here and we'll do this as a team. Okay? Right. So then I asked the question. I said, well, how are you going to analyze BMI? He said, well, I'm going to cut it into these 5 sections, and I'm going to use the normal, the middle group, as the referent group to compare everything against that referent group, which is real. That's fine. You could do that, and there's nothing at all wrong with that. But what you're doing by chopping these things up, which we tend to do a lot in medicine, more so than many other disciplines, is that you're throwing away variance. You're throwing away the variance. And if you were to just say yes, no, high, medium, low, or whatever, like, something like that, and the relationship really looks like this, you're just saying that this group is different from this group, and you have to add more meaning to that to be able to say, well, that group is lower than this group, and so on and so forth. Whereas I said to Dominique and I were talking, I'm like, well, why don't you just model the parabola? So I don't know how to do that. And I said, well, you do know how to do that. Because, you remember this? So this is just like an x squared. Right? So if you did that, then you could figure out where the nadir is of that curve there and figure out where it flips. Right? And you could actually, if you really wanted to, this is more ideas for you, you could actually figure out the derivatives of this curve and figure out at which point where the inflection points are on this curve where things are slow, increasing and speeding up and things like that. Right? So anyway, the idea of chopping things up is simple, it's easy to comprehend, and I suppose my assumption is that when you guys are treating patients and you're making decisions, you don't have time to think about, what's the nature of this variable, right? It's always, you got to make decisions like this. So that's how I believe physicians are taught, right? In science, take your time.
Do you think, I guess the other situation where we chop things up is if there's not sort of enough, numbers in each thing, almost I don't know, one of the things I'm looking at is, the number of times people check their blood sugars.
Okay.
That can be, the range is not huge.
We'll talk about that, too.
Okay.
That's the next set of models we're going to look
Okay.
at. But the idea here is when you create these artificial categories based on a truly continuous underlying distribution, you are in fact stripping away a lot of that variability in the data, and that's what we're trying to describe mathematically. So there's nothing wrong with it. You can fit your models, but be sure of or understand what it is that you're doing by creating these categories. So I talk about the fidelity of the data. By ripping out the categories, you're saying that everybody in this range is the same. When if you were to draw the parabola, that's not true. Right? So, all right. Sure how we got on that tangent, but okay. All right, so I'm just going to fit a logit model, and I'm going to say, what am I going to say? I forget what my variables are. Corin, age, weight. So I'm going to do this. All right, so this is the logistic regression. Right. What I'm going to look at here are how many observations, right? I'm going to look at my chi-square statistic. This is the stuff in the write-up. So if I were to flip to the second page of the write-up, I'll show you where I got a lot of these values from. Right, so this just describes the data set. Right, this is kind of important. So this is my paragraph of table 1, if you will, without creating table 1. So tested the full model with all 6 predictors against the intercept, the only model with statistically significant chi-square degrees of freedom 6, n equal 275, 72 1/4. Right? So remember, when we fit these models, so we have a chi-square statistic based on 6 degrees of freedom. This is my chi-square statistic. That's the p-value. So this p-value is comparing a base model, nothing. You've included nothing in the data set. When you include nothing in the data set, as a predictor, you'll still get an intercept.
Nothing meaning?
Nothing. Nothing meaning?
Absolute.
Nothing meaning nothing. So here, you can do this. Logit HA.
Or is it Corin?
Thank you.
Yeah.
That's an intercept only model.
Gotcha, okay.
All right. So if I were to take this is the average logit. If I were to exponentiate that, it would probably give me about 0.33. Does anybody have a calculator to exponentiate that real quick? So this gives me 0.57. Those are the log odds. Those are the log odds. And if I were to take that into, if I were to convert that to a probability,
Would that be
that would
point-
match the prevalence.
The 0.36 that we
Yeah,
got?
that would match
Okay.
the prevalence. Right? Because if I don't know anything about you, right, then it's univariate statistics.
Then it's like the mean is going to be
It's the
most
mean.
like, okay.
Yeah. So that's what that. Bless you.
Thank you.
That's what this p-value is compared against, or this model is compared against nothing. Is your model better than nothing? A model with nothing in it is just an intercept-only model. Okay? So this is McFadden's R squared.
And
So-
you know, it's always been said.
It's a bit for Stata, it's McFadden's R squared. There are tons of other statistics out there, but Stata reports McFadden's R squared. The reason I chose that is because that there are many pseudo R squared statistics that we could fit to the data. So if you want to be very clear and explicit, this is McFadden's R squared. So we would interpret this kind of sort of like an R squared from a linear model. So, not terrible.
Does a pseudo R squared always mean McFadden's? Or does
No.
it means it's just not a
It's not a true R squared.
Okay.
The R squared that comes from the logistic M-logit models out of Stata are McFadden's R squared. McFadden is a guy from California. He's an economist. Okay. You'll notice here that this is the log likelihood. If you were going to do likelihood ratio test where you wanted to compare one model to another, this is the log likelihood that would be used in that difference testing. And what do we see? We see that, well, taking everything else into account, blood pressure doesn't appear to have an effect on the probability of a coronary. Blood pressure height doesn't appear to be related to the probability of a coronary. But what does? We have age, older people, because this is a positive coefficient. Older people, the older you are, the more likely it is that you're going to have a coronary, holding these things constant. We see that cholesterol is positively related to the probability of a coronary. The higher your cholesterol, holding everything constant, right? And then we have weight. The more you weigh, on average, holding everything constant, the more likely it is you're going to have a heart attack. Okay? So I simply copied and pasted this and plopped that into the table.
Tim, can I ask a question?
Mhm.
So, can you just remind me why you do the log likelihood at this point after logistic regression?
Well, what's happening underneath what's happening to get these values is that, I just think, you remember when I described the concept of maximum likelihood? It was like turning dials individually, and it's actually trying to fit a function. So the function is maximized at this value. Doesn't matter what that means in particular. But if you wanted to compare, say you had another variable that you wanted to fit into the model, like treatment, right? And you wanted to control for all of these variables, then you fit another model with treatment. All of your variables plus treatment. The hypothesis you would explicitly be testing then would be, after controlling for all of these variables, does the inclusion of treatment provide any greater explanatory power above and beyond what these have already predicted? So remember when we did partial and semi-partials in linear regression? You can't do that in logistic regression because it's not the same thing, right? So we have to do these log likelihood tests, likelihood ratio tests. But conceptually, it's all the same thing. Does adding this variable add more predictive power to the model above and beyond this? That's what the likelihood ratio would be. If you just do a direct logistic regression, you can ignore this. As a matter of fact, even if you were to do the likelihood ratio test, you can essentially ignore this and just report the likelihood, the results from the likelihood ratio test.
Would you get the same coefficients?
Well, if I were to add
You
another
include the
variable,
same variables?
they may or may not change. If the new variable doesn't add anything above and beyond what these already predict, then no, these coefficients won't change. It depends on the degree to which the new variable that you're introducing into the model is independent of these, and the extent to which the new variable explains the outcome. Okay. So since these are logits, kind of hard to understand, except by looking at the coefficients, I'm going to use the OR command to turn those logits into odds ratios. Now we can begin to interpret these things. All right. So let's take a crack at age. So I have this odds ratio of let's call it 1.07. 1.07. How do you think we would interpret that?
So like the odds of a heart attack occurring increases by 1.07 for every year older,
Yes.
I guess.
Yeah. What about the other variables in the model?
And
Holding everything constant,
yes,
right?
holding everything.
Right. It increases by 107, or you could just say by 7%. Right. The odds increase by 7%. Nice and simple. And then we have cholesterol. Cholesterol is statistically significant, but now you know how we're always talking about, well, can I compare these things directly with each other? And I said, well, no, you have to think about the scale of the thing that you're trying to measure, right? Well, cholesterol, I don't know, cholesterol is going to have a whole lot more variability in it than is age in our data set, right? So we see that cholesterol being statistically significant, right? How would we interpret this cholesterol? Total cholesterol, I think we called it.
So for every 1 increase in your cholesterol, you'd have like a 0.7% increase.
Right. Now,
Because cholesterol can increase by a lot, right?
Right. So that's why it's difficult to compare coefficients directly. Could we say for every 10 points increase in cholesterol, we expect a 7% increase in the likelihood of a heart attack? Haven't we just said the same thing?
Mm-hmm.
All right. So when you have coefficients that are teeny tiny like that, help interpret that for your reader, right? Because honestly, our cholesterols are going to fluctuate in this class, in an hour, in 15 minutes. Our cholesterol is, it's going to go up, it's going to go down.
Is there any way to get a graph that has both the odds ratios and the coefficients on it?
A graph?
Like a plot, like a table.
Yeah, you have to make it.
Oh, you have to make it.
Yeah, you have to make it.
Because I was looking at the one you did and
Yeah.
it has both on there.
Yeah, I made it.
How did you get those both on there?
Yeah, I made it. Okay. And how about for weight? Do we care about 1 pound increases? Well, you might if you're tiny. Right? If I weigh 90 pounds, I do. I weigh 90 pounds.
Well, 10 pounds would be...
Yeah. What about a 10-pound increase? What happens to the probability of a heart attack?
20%.
Yeah, for every 10 pounds one gains, the likelihood of a heart attack increases by about 20%. Now we're talking, right? Now we're talking, right? I can't control somebody's age, like that's how old they are, right? But let's assume that these data are real. Do we have any cardiologists in the room? Any cardiologists?
What? I am not. What?
You're a cardiologist. So looking at these data,
Yeah.
let's assume that the data were real.
Yeah.
What would be the thing that you would tell your patients? Can you tell them to get younger?
Nope. Get on a statin.
No, George.
Oh.
It's called they call it Rab. I'm not taking a statin.
But
Lose weight.
forever
Just say
10.
Lose weight.
Lose weight.
Yeah, that doesn't work. No either. I'm a big believer in pills.
Okay. True American. Yeah, right. All right, because we probably these things, right? So we say that blood pressure probably. How would we interpret these things that are not significant? We have blood pressure. Blood pressure does not appear to be related to heart attack, in the presence of these other variables. How would you interpret that?
Well,
This is-
meat can definitely elevate blood pressure, so perhaps that's why we're not seeing a relationship with blood pressure.
Right. I don't know. I mean, this is where subject matter expertise comes in trying to interpret these coefficients, right? If we were talking about this with respect to partials and semi-partials, we'd probably say that weight is going to account for a lot of that predictive power of these two things because it's going to be related to both. It's going to be related to blood pressure and the outcome.
Aren't you holding everything else constant?
Yeah.
Right,
So by holding it constant, you've removed it.
right.
When you see this and you see that you have certain variables that are not significant, would you, in your next step then, like when you have your final model, just drop the variables that weren't significant?
It depends what the question is. That's why we talked about it in the beginning. My question was, I'm interested in how all of these variables work together to predict the probability of a heart attack.
Okay.
So my hypothesis was all of them simultaneously.
Okay.
So I would stop here. If I was interested in prediction alone, and I had a lot of money, because how much does it cost to do blood pressure? It's marginal, right? It's marginal. So for the things that are not significant, blood pressure, blood pressure and height, you're going to do that as part of your, if somebody walks in your office here, step on the scale, put the cuff on your arm, right? That's what you're going to do. So it doesn't cost any money, extra money, to collect these data. It's not going to hurt your model by including these in your prediction equation. But here I'm thinking about this not from a logistic regression, but a logistic sense. It's not going to cost me any extra money to capture the data. And it will give me a little bit more predictive power. Sorry, go ahead.
No, I was just going to say, just based on what we were just talking about, I mean, what if we wanted to take out the weight variable to see if there is, maybe now, an influence on blood pressure and heart attacks? Could I just take out that variable and see if, okay, now I'm not controlling for weight?
Yeah, sure you could.
And just go through it that
That's
way?
a different hypothesis.
Right.
Yeah, which is why, and that's great that we're thinking now, right? We're thinking about things, but that's what we need to do. We need to ask, what is the question? My original question was, how do all of these variables? If we wanted to ask the question, what is the effect of weight above and beyond these other things, then that's a different question. Okay.
Could you report, Tim, I feel like people report there was a positive relationship between systolic blood pressure and risk of the outcome, but the sample was too small, it was a non-significant positive relationship, and conclude that there might be something that you didn't have a highly enough powered sample to discern it.
So what you're doing is you're engaging in what we call a post hoc power analysis. That's like hindsight. You don't get credit for that. Doesn't stop people from doing it, but it's okay. That's like me giving you the answers to a test and say, here's the test. Is it meaningful? Not really. You already know the answers. To then go back and say, oh, well, if I had more patients. This would be helpful for designing your next study, but these are the results of this study. It drives me bananas when I read in articles, this was approaching statistical significance. What does that mean? I don't know what that That means that's breaking the rules of the game that we set up. If you chose your alpha at 05, then it either is or is not statistically significant. There's no approaching.
Do you feel the same way that people say like there's a trend towards this?
Well, you can actually test a trend.
Okay.
Right? So if I have a cat, like in the case of what Dominique and I were talking about, if we could actually, remember that, all those, the contrast matrices that we were dealing with? The next step would be to do quadratic trends and polynomial trends in the data with these categorical outcomes. And you can actually test to see if there's a trend. Now, is this tending towards rejecting the null hypothesis? I don't know. Right, because then the other thing I could look at are my confidence intervals. So how did I get those other statistics? Do you guys have the source code that I gave you from previous classes? So this is going to be the thing that you're going to the thing that you're going to want. It's E-stat classification. That's how I got my positive and negative predictive values. E-stat space classification. This is where I got my negative and positive predictive values. So how's our model? Well, it's what?
I said a little shitty.
A little, did you say a little shitty or a little shady?
Shitty.
Shitty, yeah, it's not so good, is it? Even though we had statistical significance, you know, you're doing a little bit better than flipping a coin if you test positive on our little things here. If I want to get the receiver operating curve, this is the ROC curve. So, we capture about 79% of the area under the curve here. We could probably do better. So that's where I got those values. So to Arthy's question, I actually built this table. I just, in Excel, I just added another column, exponentiated these values to get my odds ratios. Right?
Okay.
That's all I did. And then here are my my verbalization of the table. Okay. Okay. So that was your homework. And where did we leave off with the multinomial stuff? We did the multinomials, right? Did we do the ordered logit?
Yeah.
Okay, so in this case, where we left off, I think, so did we get to the continuation ratios?
We stopped
I
in
think-
that. We stopped in the ordered logit.
Yeah, I think we
stopped
talked about the concept of the ordered logit, but I don't think we went through like the actual.
Okay, so let's talk about the ordered logit. Okay, so in an ordered logit, so here's another problem, is that a lot of these models have synonyms or different names for the same thing. So, what we're talking about now is something called a cumulative logit, or an ordered logit, or what some people call a proportional odds logit model. And what we're going to do now to sort of motivate this example is that we're going to be interested in looking at the effect of marriage on one's self-reported level of happiness. Just because it's fun, okay? So in this case, let's take a step back and think about the nature of our variables here. Okay, so here we have our crosstab, where we're going to look at marital status. This is our predictor. And our criterion is self-reported level of happiness. So before we even look at this, let's talk about happiness. When you think of happiness, what kind of variable do we think of? Are you happy? Yes, no. Who said that? Yeah, you think of it as a sort of this continuous thing, right? People aren't happy or unhappy, right, generally, right? We think of them, at least most people, I don't know about you guys, kind of weird. Most people think about happiness as sort of being on a continuum, right? On a continuum, that could be, you can think of ultimate elation on one end of the scale to the ultimate depression, I suppose, on the other end of the scale, right? So thinking about this operationally, it would be really difficult to come up with an awesome measure of happiness where we could put everyone perfectly on that continuum of the scale of happiness, right? So what we tend to do, because we're fallible humans, is we try to make life easy on ourselves. So what we've done is we've come up with a scale, and we ask people to respond to these stimuli. Well, how happy are you? Your choices are not very happy, happy, very happy, right? Does that encompass all levels and degrees of happiness? No. What is it? It's an artificial categorization of the data, right? So what we're going to try to do with these cumulative logits, or another way to think about this, is that if we think of these categorical outcomes as being really artificial categorizations of some continuous variable, then we can conceptualize the model a little bit differently, right? We might think of happiness as what we refer to as a latent variable. I can't taste, touch, feel, or see happiness, but what we see are the consequences of happiness. Okay, makes sense? Like blood pressure. Do you actually measure blood pressure? No, you don't. When you put a sphygmometer, you study the consequences of blood pressure. To study blood pressure, you actually have to put something into the artery, right? So when we put a cuff on somebody, we don't measure the blood pressure directly. We're studying what we believe is the evidence of that thing that we call blood pressure. That's a latent variable. The way that we measure blood pressure in the clinic is a latent variable. We're studying the consequences of it. We're not studying it directly. Okay, so with respect to this ordered category here, we can sort of scale this thing, and let's say that, for the sake of argument, that we're going to think of happiness as this continuous variable, and to give some sense to this, let's think of 0 as being the average level of happiness, right? Anything below 0 would be towards the unhappy end. Anything positive would be towards the happier end, right? So what we do with these cumulative or ordered or proportional odds logits is what we're going to try and do is we're going to try and estimate where somebody is on this continuum with respect to how they respond to the test. Okay? Now, this is what makes the model a proportional odds model. Okay? So what I've drawn here, we can think of it this way. So if we're talking about what's the probability that you're in the not very happy category versus the other categories, right? So that would be one threshold. This would be a threshold. So what is the point at which it becomes Can you see this on that end, over there? So if I were to think of this as a probability of responding, right? Where is the point at which it becomes a 50-50 proposition of responding not happy versus something else? You with me? What point does it become a coin flip? So that's one thing that we're going to think about. The other thing we're going to think about, and this is the very strong assumption, this is an assumption of the proportional odds model, is that this is drawn very poorly, but imagine that these two S curves looked exactly the same. The assumption here is that the slope of these two curves are exactly the same. The slopes of those curves are the same, because remember, the slope would be the beta coefficient in a logistic model. Okay, so if the slopes are the same for each of these curves, the only difference between this curve and this curve is the location, then I'm making an assumption that the odds of being in this category versus the higher category is the same odds as being in the lower category versus the higher category up here. Make sense? So a simple way to think about it is, it doesn't matter where you are on the continuum, the odds of being in the lower group versus the higher group are the same for the married versus, or the difference in the odds for the married versus the unmarried are the same regardless of where you are on the continuum. Okay. Let's fit the model and we'll make some sense of this. Maybe. Okay, so what I'm going to do is we had some data. I think I gave you the source code for all this last week. So, all right. So what I'm going to do is I'm going to use the O-logit command for ordinal logit. Now I'm going to regress happy onto married. Here's my chi-square. All right, my chi-square based on 1 degree of freedom. What is this chi-square testing?
Oh, it's better than nothing.
Better than nothing, right? And what is this R squared? Still R squared? It's McFadden's R squared. All right. So here's what we have. We say, aha. We have a positive logit. It's going to be huge. A logit of 1, that's going to be big. So what does this say? This means that people who are married, as you go from unmarried to married, the association is positive. People who are married are more likely to be in the higher category as compared, relative to the lower category of happiness as compared to unmarried people. You with me? Okay. So, I actually have 2 equations here. I have 2 equations here. So I'm going to have an equation of, what was the least happy? Not happy. Not happy. Versus happy or very happy. All right, that's my first equation. So what I've done is I've, in a sense, collapsed the top 2 categories, and I'm going to compare that to the lowest category. And then the second equation is going to be not happy and very happy. I'm sorry, not happy and happy versus very happy. Okay? That's essentially what 2 equations that we fit simultaneously using this model. So the first model the equation is going to look like this. It's going to be negative 1.46. This cut is an intercept. This is the intercept. Plus 1.002 times n for married. All right, so if we were to write this out, we get this equation here. And if we were to exponentiate 1, so what happens when I exponentiate 1? You have a calculator? Was it gonna do?
2.7.
2.7, okay.
2.72.
Okay, 2.7. So I'm gonna write down EX1 is about 2.7, okay? So what we're saying here is that back to our threshold. We're saying that on this threshold, on or about negative 1.46, this is the point at which it becomes a 50-50 proposition of answering not happy versus something else. So anybody below a logit of negative 1.46 is far more likely to report being unhappy. Okay. Now, this is the threshold for the second cut point. So now we've now taken this continuous function, and now we have unhappy, happy, very happy. Okay? Make sense? So at this point, 1.35 becomes the threshold at which it becomes a 50-50 proposition of people who are at this point, along this point on the continuum of happiness, of saying, well, I'm either very unhappy or not. Anybody above here on that threshold of happiness is much more likely to say very happy. People below this threshold are likely to report something else. However, the other thing that we have in the model is the coefficient here. So this says that married people are 2.7 times more likely to report being in the happy or very happy group relative to the unhappy group as compared to unmarried people. Because we have the proportional odds assumption here, that same odds of 2.7 says that married people are 2.7 times more likely to report being very happy as compared to unmarried people. That's a strong assumption, a proportional odds assumption. So, right, if we understand this concept, this 2.7 we're saying is consistent across the entire range. Our 3-point scale just happened to make the cut points here. If the proportional odds assumption were real and our model was perfect, let's say that instead of a 3-point scale, we had a 4-point scale, and we added another curve here, right? It would also be 2.7. If we had a 5-point scale, it would also be 2.7.
Right, and that's just between the two. You said married are 2.7 times more likely to report being
In the higher category versus the lower categories.
And just adjacent ones or anyone?
Anyone, at any point on the
If there were
curve.
5, it would be in the top, the 5th versus all of them, or 4.
Yes, and the married people would still be 2.7 times more likely to report being in that group as compared to the unmarried people. Strong assumption. It's a very strong assumption. Okay. But if we begin to think about our variables and the nature of our variables, we can begin to tell a much more interesting story with the data as opposed to yes, no, happy, unhappy, so on and so forth. Okay. All right. Okay, so then we have the next, yes, sir.
Sorry, maybe you're going to talk about, but how do you test whether that proportionality
the proportionalized assumption fits the data, there's another test for that. Remember, what I wanted to do here was just give you a flavor, or a flavor, we call it on statistical streets, yellow, of what's out there. Right, there's another thing called the adjacent categories model. And what we're going to do is we're going to go back to the birth weight data again. And then instead of saying low birth weight, normal birth weight, not low birth weight, what we're going to do is we're going to break the categories, and we're going to further break down those categories here. Okay? All right, so what I want to do is I want to look at the relationship between smoking status of the mom and which birth category the little person came out of the oven was. Okay? All right, so one thing that what we should probably notice here, is that I have actually recategorized the variables. So what I have done is I've made the highest, instead of, so if these are nominal data or ordinal data, in the past when we first did this, 0 would be low birth weight, 1 would be not low birth weight. I flipped things around such that 0 is going to be the highest birth weight category. And the reason I did that was because I want this group to be the referent group. I want the low birth weight group, the lowest birth weight group to be the referent category. Okay. So this gets kind of confusing. But what I'm going to do is I'm going to, I have to make some constraints here. Right. So essentially what I'm going to do